If your high schooler is going into geometry this year, I'm guessing the only tool on their back to school shopping list was a compass like this one. But I don't see how anyone can learn geometry without physical manipulatives. Geometry is all about the properties of shapes. It's about size, distance, and position of figures in space. So I think in order to learn that, you need to have figures in space. Although I believe Eratosthenes calculated the circumference of the earth using only a stick. But we can't all be ancient Greek geniuses. I use a lot of tools when I tutor geometry, and I want to share with you the top 3 that I think every student should have. The first is geometry sticks. These are super versatile. You can make any polygon with them by connecting sticks. And you can use them to see the relationships between side lengths and angles in different shapes, and how changing an angle affects the length of the sides or the other angles. A trapezoid is a kind of quadrilateral, so all of the angles sum to 360 degrees. And if I have a smaller angle here and a larger one here, if I were to change this angle to make it larger, it forces this one to become smaller. So you still have 360 degrees. Let me ask you this. Do you think you can make a triangle with any 3 line segments? A lot of students assume you can, but when they play around with geometry sticks, they discover that sometimes you can't. This won't form a triangle. You can't use this whole stick. And one of the most basic principles in Euclidean geometry is the triangle inequality theorem, which states that the sum of any 2 sides of a triangle must be greater than the third side. And now you can see why, because when I add the orange and green side together, it's not as long as the red side. These 2 purple sides are the same length as the red side. Will they form a triangle? Well, if they're the same length, then the problem is when you go to make an angle, there's no give. You can't make a triangle with these. And so you can really understand why the sum of any 2 sides in a triangle has to be greater than the third. Next on your list is a set of solid figures. These are essential for learning volume, surface area, and lateral area. And you want to get a set where the shapes can open like this. Students usually memorize the formula for the volume of a cylinder, which is pi r squared times the height. Pi r squared is the area of this round base, and then you multiply it by the height of the shape. They also memorize the formula for the volume of a cone, which is 1/3 pi r squared height. But what this means is that if pi r squared is the same in both, meaning the area of the base, so these 2 bases are the same, and the height is the same, so these 2 shapes have the same height, then that means that the volume of the cone is 1/3 the volume of the cylinder. It takes up 1/3 of the space of the cylinder. That means this one has 3 times the capacity for water at the cooler than those little cone-shaped cooler cups. The same relationship applies to a square prism and a square-based pyramid. So you have same base, same height. That means that this pyramid can hold 1/3 the volume of this prism. Finally, the hinged mirror. It's really useful for symmetry, especially rotational symmetry, and for reflections when students are doing their unit on transformations. If a student is asked to find the reflection of this shape, one way to do that is to hold a mirror wherever the line of reflection is, whatever line they're supposed to reflect the shape over, and you can see what it will look like on the other side. So then I can see that this would be the reflection of this shape. Where students run into trouble is when they're asked, is this a correct reflection of this? Some students will say yes, but when you look in the mirror, you can actually see that the shape is facing the wrong way, that the actual reflection of this shape would look like this. One reason for using a hinged mirror is because it really comes in handy for topics like rotational symmetry. So a shape has rotational symmetry when you can rotate it around its axis and the shape will come out looking the same as it did to start. A hexagon has rotational symmetry with order 6. When you rotate it 6 times, 1, 2, 3, 4, 5, 6, it comes out exactly the same. And each time I rotated it, I turned it 60 degrees. Now, I know that the angle of rotation is 60 degrees because of a formula, but if you want to test this, you can do it with the mirror. So you get a protractor and you open the mirror to 60 degrees. Then you put the hinge of the mirror at the center point of the shape. And when you look in the mirror at the reflection, you should see the original shape. So in addition to all of the notebooks, binders, and pens that you have to buy your kids before they go back to school this year, let's prioritize physical tools for math so we set kids up to really be able to understand geometry concepts.